So we were discussing uh, the use of a current control current source to make a better common source amplifier, right? So what was the genesis of it? A 5-minute recap for the same is, so we knew that this is the structure of our common source amplifier shown without biasing. We have VI, the incremental current GMVI flows entirely into the load and generates a voltage GMVI times RL, negative of that. But this assumes that very simplistic model of the MOSFET, where we assume the output conductance of the MOSFET is 0, or its own internal impedance is infinite. Or in other words, we assume that it's MOSFET is an ideal current source. Okay, so then we in couple of classes back we saw that that is probably not a very good assumption to make under certain scenarios. So which essentially means that we have to modify the small signal model, and if we modify the small signal model of the MOSFET, an additional resistance or a conductance appears in parallel to the MOSFET. The way I am sketching it, it essentially means that the symbol represents an ideal control source, and the non-ideality is being taken out and put in parallel. That is, the non-ideal GDS is being taken out and put in parallel, just for the sake of clarity. Okay, so if this is the situation, then naturally all of this GMVI will not flow into RL. It will get diverted between if I say GL and RL. Between GL and GDS, and the diversion will be proportional to the conductance ratios, right? So in this case, if you see that GDS is of the order of GL or higher than GL, then bulk of the incremental current that is getting generated will flow into GDS and not into GL, which is a problem because we ultimately want all the incremental current to flow into the load. So the solution that we came up with was connecting here directly is a problem. So we cannot connect directly. So we have to put something here which can give an impedance such that all of this incremental current GM times VI flows into that box, right? Which means we need something which has a low input impedance, low with respect to the impedance of the transistor itself. And we saw that, I mean, a few lectures before that, we spent some time figuring out what type of sources give what type of impedances and so on. And in this case, looks like current controlled current source is the obvious choice. So then we replace this box with the current controlled current source that we know of. The only current controlled current source that we have extensively studied is the common gate topology, right? So if you have a common gate topology where the gate is incrementally grounded, again, this is an incremental picture, not the biasing picture. If the gate is incrementally grounded, then we know that this impedance, we knew that this impedance is 1 over GM, right? If we neglect the GDS of the common gate transistor, right? So again, just for the sake of clarity, if I look into the impedance of the common gate transistor, that is looking into the source, this impedance Rin is 1 over GM. This is assuming M2 has GDS, which is 0, right? This is assuming M2 has GDS is equal to 0. But if M2 doesn't have a GDS equal to 0, which is an assumption that we shouldn't make, right? Which is an assumption we shouldn't make, because if we had a transistor whose GDS was 0, I would have used that in the first place, in place of M1. So if that is not true, then let's say we modify the transistor M2, which has a GDS 2 in parallel to it. Then the Rin we saw, Rin is approximately equal to 1 over GM plus RL divided by the intrinsic gain of M2. Right, I should say I int, right? Intrinsic gain of M2. Okay, so I mean, which essentially means that if intrinsic gain of M2 is infinite, Rin becomes 1 over Gm or 1 over Gm2, right? And again, just to ensure that we are all in the same page, if GDS is equal to 0, what is the intrinsic gain of a transistor? Intrinsic gain by definition is a gain that a transistor will give if it is loaded with an open circuited load, which essentially means that, let's say I have a, this is the configuration incrementally. So what will be V naught over Vi? Pardon? Again, think incrementally. This is not full. RL is infinity, true? No, now we have GDS. Yeah, GM over GDS. Oh, why? GM into RDS. Right. So again, so if this symbol makes you uncomfortable, so what is the incremental picture of the transistor with GDS? Vi, this is GMVI. This voltage will be minus GMVI over GDS. Right? So incremental gain is essentially VDS over VGS when RL is infinity. Right? So this is equal to minus GM over GDS. When we neglect GDS, right? When we neglect channel length modulation, the intrinsic gain is what? GDS is what? If we neglect channel length modulation, what is GDS? 0, right? So intrinsic gain is infinite, right? Yeah, so that's an ideal transistor, which gives you infinite intrinsic gain. Okay, so if we have an ideal transistor, then the intrinsic gain goes to infinity and Rin reduces to whatever it was meant to be, right? But if you don't have an ideal transistor, in this case, the looking in impedance into the source of M2 is 1 over GM2, whatever we wanted it to be, plus some additional term. And the additional term is not equal to RL. It's an RL which has been divided. The value of the RL has been divided, has been reduced by a factor of the intrinsic gain of the transistor. Okay. So even though this transistor is not able to fully shield RL from M1, right? The whole purpose was to shield RL from M1. The current control current source ideally should be able to give us a low input impedance in such a way that whatever is connected to the other side of the source shouldn't matter. But in this case, it looks like it still matters, but it doesn't matter as much. So your Rin is now, in the absence of M2, Rin would have been RL, right? In case of a normal common source amplifier without M2 being connected, Rin would have been RL. But in this case, Rin is RL over the intrinsic gain of the transistor plus 1 over GM, right? And good thing about this is these are all user control parameters, which means, or rather designer control parameters, which means that you can size the transistors, bias it in such a way that Rin becomes much lesser than 1 over GDS, right? Because you want all the current to flow into the flow into M2. Okay, fine. So another thing, another useful thing to recall is, just like we know that, so these are some of the topologies which make regular appearances. So there are some things which you need to by heart. I mean, you can always write KVL, KCL to figure it out, but it's just that it takes more time. So For example, what is the impedance looking into the drain of a transistor when we are when the gate and the source are incrementally grounded? Pardon? It's infinite if we neglect channel length modulation. If we don't neglect channel length modulation, which means you have an RDS, what will be I shouldn't say R in, I should say R out maybe in this case. What will be R out? RDS. If we have if we look in through the source, what is R out? 1 over Gm in the absence of GDS of the transistor. If we have GDS of the transistor, then this becomes whatever RL divided by the intrinsic gain. Right? So the reason I'm writing this out every time, these are some of the useful expressions which you will find it handy just to reduce the algebra. Okay. I mean, again, one might say that the example that I give is just if you go back to your school days, early school days, when you used to learn tables, right? Tables of, I don't know, from 2 to 19, or I don't know how much do you learn nowadays. There's no reason of learning tables because we know that 6 into 4 is 6 plus 6 plus 6 plus 6, but we still learn the table. Why? Because it makes our life easy. Right? It's the same thing here. Okay, fine. So now going ahead, this is this structure. So again, the difference between this structure and this structure let me not write it immediately. Let me say this is incrementally grounded. Since we are doing all incremental. The difference between these two structures is the fact that the amount of short circuit current, right, or the amount of current that is flowing into the load in the structure is higher in the structure on the right than on the structure on the left. Because this current Gm times Vi, which is getting generated in both cases, in the circuit on the left, only a fraction of Gm times Vi flows in because the other fraction flows into the GDS. But in the structure on the right, bulk of the, or rather a significant fraction of Gm times Vi can flow into RL if the top transistor is sized properly. Okay. So now, in other words, what we are trying to get to is we are trying to make a better a better voltage control current source, right? So the reason I say that is if I black box this structure and if I black box this structure and we only look at the expected terminal characteristics, what are we expecting? We are expecting that I will apply a voltage Vi and a voltage proportion and a current proportional to Gm times Vi should come out of the box. That is the expectation. Now, because of some internal characteristics of the transistor, a fraction of Gm times Vi is coming out. Okay. Other way of thinking about it is in the structure on the left, right? In the structure on the left, what is the output impedance? So let me now get back to the output impedance discussion. So this is grounded. If I try to look into the output impedance here, what will be the output impedance? If GDS were 0, what would have been the output impedance? No, right? It would have been 1 over GL, right? Conductance would have been GL. So let's not bother about GL because it is common in both cases, right? So let's find out the output impedance looking down. into the transistor. So looking down into this box, this output impedance is 1 over GDS or RDS. Or 1 over GDS. Okay. But if RDS is not large enough, right? What is enough depends on what we are comparing it with. But let's say RDS is not large enough, then this is not a very good current source, right? A current source should have a very high output impedance, ideally infinite output impedance. So what about the structure on the right? I mean, now the middle, right? So what about the structure on the right? If this structure is supposed to behave like a better current source, a better voltage control current source, then it is expected that its output impedance should be higher than RDS, right? So what I would request you to do is now calculate the output impedance of this structure, incremental output impedance of this structure. Obviously, in this case, you have to assume you have some GDS. Let me call this RDS2, RDS1. You can assume this to be GM2 and this to be GM1. And the way you do it is you apply a test voltage and find out the test current in terms of the test voltage and take the ratio. So please do the calculation. Okay, so how do you go about doing it? I mean, let's take one by one. Obviously, this transistor goes out of the picture because its VGS is 0, right? If VGS is 0, only the GM part of the transistor goes out of the picture, not the RDS part. Okay, so that goes. So I'll just delete it from here. So ITest flows from this side, which means ITest has to flow out from here. So which means this voltage becomes ITest times RDS1, right? So if so this current becomes what? Minus GM4 times this, so sorry, GM2 times 0 minus ITest times RDS1, right? So which means it's negative of that flowing upwards. So we can do a KCL at this node now. KCL at this node gives us what? It gives ITest plus GM2 times ITest times RDS1 is the amount of current flowing into the node is equal to the current flowing out, that is VTest minus ITest RDS1 divided by RDS2. Okay, so if you now do the algebra, what you should get is VTest over ITest should be RDS1 plus RDS2 plus GM2 RDS2 times RDS1. Let's verify whether we're getting this or not. Okay, so let's stare at this equation for some time. So let me rewrite it. So R out in this case becomes RDS1 plus RDS2 plus I will rewrite this expression in a slightly different way. This GM2 times RDS2 is essentially the intrinsic gain of the top transistor, right? So this seems like GM4. The GM2 times RDS2 is the intrinsic gain of the top transistor. So I'll simply write it as an intrinsic gain of the top transistor times RDS1. Okay. Again, a very important expression which we will use multiple times later on. So now let's do a sanity check first. The quick sanity check is, if M1 were ideal, that is the bottom transistor were ideal, right? What was the expected R out? Infinity, right? So if bottom transistor were ideal, then RDS1 would have been infinity, then R out would have been infinity. No issues. If the top transistor were ideal, what is the expected R out? Infinity. That also checks out, right? So the easy one checks out. Now, if I just look at this, if I eyeball this this schematic, then the obvious thing that should stick out is it looks like RDS1 and RDS2 are in series, right? Looks like RDS1 and RDS2 is series. Not exactly true, but it looks like that, right? So it is expected that R out should have these terms of RDS1 plus RDS2, right? Because, for example, if GM2 were 0, right? If GM2 were 0, then the output impedance would have been RDS1 plus RDS2. Do you agree? So if GM2 were 0, then intrinsic gain of the second transistor would have been 0. Then I should get RDS1 plus RDS2. That also checks out. Okay. So sanity check is fine. So now let's get into a bit more of detail. So what does this expression then is trying to tell us? It's trying to tell us that when you put a common gate over a common source topology, or we are looking at a stacked transistor output impedance, this is one transistor stacked over on top of another, then the output impedance is not only the addition of the internal resistances of those two transistors, but there is an additional term. And looks like the additional term can be the dominant term, right? If the intrinsic gain of the top transistor is more than 1. And it is expected that the intrinsic gain of the top transistor will be more than 1 if you bias it in saturation, right? It can be much more than 1. So if it is much more than 1, then R out essentially looks like it becomes this almost becomes equal to, this is not true under all circumstances, but when the top transistor is in saturation, this almost becomes equal to the intrinsic gain of the top transistor times the load that is connected to the bottom transistor, right? Or the bottom transistor RDS. Okay. So why is this important? Firstly, what is the intuition behind this, and why is this important? So this is important because this looks like, I mean, this definitely is much greater than RDS1, right? So this, we expected this contraption to behave like a better current source, which means we expected this contraption to have a higher output impedance. So first thing checks out that at least it has a higher output impedance if both the transistors are in saturation. Okay, that's good. So now the question is, why so? Why? I mean, math checks out, but why is it actually that you have high output impedance for this case? So to appreciate that, we have to do an apple-to-apple comparison, right? In both cases, we have to figure out if I put both these cases together, what is the output impedance in both cases, right? So let's do that. So in this case, we are applying V-test. You have RDS1. So in the circuit on the left, the voltage across RDS1 is the entire voltage that you have applied, right? Simple case. So firstly, these two transistors don't come into picture because their VGS is 0. So in the case on the left, VTest appears, entirety of VTest appears across RDS1. Hence, the incremental current is VTest over RDS1. Hence, the resistance is RDS1. Quite trivial, but you'll understand why I'm stressing on that. So the circuit on the right, if I have to do a comparison between the two structures, it is instructive to understand what is the voltage drop across RDS1. Right? If the voltage drop, can you comment on, without doing the calculation, can you comment on the fact, what do you expect the voltage drop across RDS1 to be? Could it be higher than the case on the left or lower? Lower. It has to be lower, right? Because the calculations that we did earlier was telling us that the output impedance is high, which means the amount of current I should be able to draw in will be low, right? So if this analysis can show us the voltage drop across RDS1 is lower than the one on the left, then that would also satisfy the case as to why the impedance in the structure on the right is higher than the impedance on the structure on the left, and it will also give an intuition as to what fraction it is lower. Okay, so the next thing that what I want you to do is to tell me what is the voltage at this node, right? So you can borrow the calculation from the previous part and tell me what will be the voltage at this node in terms of VTest, obviously. So the impedance looking to the output side is this, right? This is what we calculated. So the current will be VTest over R out. This current flows here. So the voltage that is getting accrued is VTest over R out times RDS1. And if I use a simplified expression for this, so this becomes VTest over the intrinsic gain of M2. Right? So looks like in the circuit on the right, the voltage across, that is the voltage that is developing across the bottom transistor is one intrinsic gain, is lower by a factor of one intrinsic gain than the voltage that is appearing in the circuit on the left. Right? So this is almost, I mean, do you see that? Okay, so this is the analogy that I gave. You can think of the circuit on the left as being exposed to the entire voltage swing. Since the circuit on the left, without the top transistor, is getting exposed to the entire voltage swing, it has nothing else to do but to accommodate for the current that will that is VTest over RDS1. But in the circuit on the right, there is a top transistor acting like a big brother shielding the little brother, right? So the entire voltage swing, most of the voltage swing is dropping across the top transistor, and it is protecting the bottom transistor from bulk of the voltage swing. And how much it is protecting it by? It is protecting it by the intrinsic gain of the top transistor. Right? So the voltage swing across the bottom transistor is getting reduced by a factor of the intrinsic gain of the top transistor. Hence, the amount of incremental current that is flowing through the bottom transistor is also low. Hence, there is a high output impedance. Okay. Okay, fine. Any questions till now? Yes. Okay, so let me answer that question. I'll come to that. So her question is, why am I directing the low voltage swing to high output impedance, right? So that relationship is not true all the time. What I'm trying to do is to figure out how much incremental current is appearing, right? So in the circuit on the left, what I'm trying to do is apple to apple comparison, in the sense that I would want, in both the cases, I will look at M1 and try to see what is the current that is flowing through M1. Okay, so if I know that GM of these both cases are not coming into picture, GMs are off. The only thing that I have to look at is RDS1, right? And don't think of RDS1 as intrinsic resistance. That is RL, some resistance, some RL. So now, if I have to figure out the current through RL or whatever the resistance that we are trying to figure, All we have to do is to find out what is the voltage swing across that resistance. If I know the voltage divided by current is resistance, right? So what we are trying to do is essentially, if we can establish that the circuit on the right has lower current for the same BTS that has been applied, then the circuit on the right will have a higher impedance, right? So we are trying to break it down into trying to figure out why is it like, okay, I get the checksum, but why is it the circuit on the right has a higher output impedance? If it is indeed giving a higher output impedance, then after I look at the same transistor in both circuits, then the circuit on the left will see higher voltage than the circuit, because it is only then the right circuit will have a lower. That's the whole argument. Yeah, your question was, if I put up a circuit like this, it seems like the water transistor can go out of saturation. 100% it can, but the job of the designer is to ensure that it does, in the sense that how do I bias the top circuit with the circuit on the right is the two transistors stacked on top of each other, right? So that is the next thing, right? So you have already done that in some of the assignments. So we'll before I come to that, any questions on this? Okay. Yes.
So within the middle that becomes low.
Yes.
Not the question voltage.
This is all incremental. I haven't, so even though I have one transistor.
So why is there a problem with saturation?
But there is no. I think his question is, if we put it like this, then in the question mode, it can go out of it, right? So again, I mean, since we are talking about going out of saturation, so that expression that we wrote, right? This expression that we wrote, this has nothing to do with whether the transistor is in saturation or not, right? These are generic terms. If it is in saturation, then RDS1, RDS2 will be very large. If it is linear, then this term will be very small. But this expression is still. Now let's assume the top transistor, that is GM2, the corresponding GM2, goes into linear. I was not careful in biasing in the question state. That goes into linear. Then which term in this expression do you think will suffer the most? RDS2 will suffer, and by extension of that, the intrinsic gain of the transistor will also suffer. Which means the major term, which was A2, is going to drop, because the GDS of a transistor, Y2 of a transistor, which is a linear region, is quite high. Its intrinsic gain is low, right? Since the intrinsic gain is low, that major term, which is giving us this high output impedance, is going to vanish. Right? And extreme cases, let's say this goes into, extreme case of a transistor going into linear region in the quiescent state is BDS close to 0. Right? If BDS goes close to 0, it is almost like this transistor doesn't exist. If that gets shorted, then you expect the output impedance to be only the impedance of the bottom transistor, that is RDS1. That's what is going to happen. So if you will not be watts with respect to a common source amplifier, but you won't be any better. If the top transistor is not biased properly. Okay, so let's now get to the biasing picture. So this should be easy because we have spent a lot of time in figuring out how to bias these type of topologies. So firstly, the bottom guy has to have VGS. I'm showing with respect to a battery, but we know that there are multiple ways of implementing this. So this can be some VGSQ. So let me use the current source bias itself. This VGSQ I can develop from another diode connected topology, which is connected to a current source, right? And then we can do all those things, right? AC couple. So these are the usual things we have been doing so far. Nothing new here. So given that this is VGSQ and the value of the current corresponds to I naught, the question then now boils down to how do I bias M2? Okay, so this is M1, this is M2. How do I bias M2? What will be rather this VB2 to ensure that both M1 and M2 are in saturation? Okay, so one piece of advice while doing these type of calculations is to the first order, you can neglect channel modulation when you are doing Poisson calculations, unless explicitly mentioned. Okay, so the reason I'm saying that, otherwise we'll end up with third order equations, right? Because you have like VGS minus VT whole square times 1 plus VDS. VDS becomes dependent on VGS, and then you end up with cubic equation that is no good for anything. So generally we tend to neglect channel modulation, that 1 plus lambda VDS term while calculating Poisson, unless otherwise mentioned. Okay, so we'll do the same thing, right? So we'll neglect while doing calculations for Poisson's sake, we'll assume that there is no effect of channel modulation to the first order. In some cases, we cannot make that assumption, but so far we can make. Let's make that. So if that is the case, what will be what is it that that is necessary to ensure that M1 and M2 are in saturation? Now this should be pretty obvious. Tell me. So let's start with M1. VGSQ, let's assume is sufficient. Okay, whatever is necessary. So what is it that we need to look at to ensure M1 is in saturation? Yeah, so right, VD1. So what is the minimum VD1 that is necessary? Right, so VD1 minimum, or rather VD1 should be greater than, I would say, V overdrive of M1. Right? So then how do I go about figuring out what will be the VD2? Will any value of VB2 be fine? No, right? So there will be a range of VB2. There will be a minima, there will be a maxima, right? So let's figure out what will be the minimum.
We find the current,
Right?
then we find the voltage at the drain of M.
We find the current, then we find the what is the drain of M2. Your point?
V equal to VT plus VGS.
Yeah. So this point is if I find the current and find the drain voltage that VD1, right?
At the drain of M.
Drain of M2. Okay, we'll do that. But what will you get from that? You will get the maximum or the minimum. You get the maximum of VB.
So we need a condition of greater than VB2 minus VD2.
Didn't understand this. Why did you say so?
The drain voltage should be greater than the overdrive.
You are talking about this drain voltage or VD1 drain voltage? VD2. So, okay, so I'll come to VD2, right? So let's only concentrate on VD1 and try to figure out VB2, right? So think of it this way, right? So if a current of I0 has to flow through M2, the VGS, some VGS has to develop across it, right? Across the VGS of M2, right? So if that voltage has to be developed, then if we know the expected source voltage of M2, that is VD1, then I should know what will be VB2, because VB2 is the source voltage plus the VGS, right? So if VD1 has to be greater than VOV1, then VB2 has to be greater than VD1, or rather VOV1 plus VGS of M2, right? So what is VGS of M2? I can write VGS of M2 as threshold voltage plus 1 overdrive, right? So essentially this becomes VOV1 plus VOV2 plus the threshold voltage of M2. Okay, so assuming M2 is in saturation, what happens if I keep on increasing, if I keep on modulating VB2? If I increase VB2, what's going to happen? I'm not modulating it by a large amount. It's a small increments of VB2. What is going to change? Is current going to change? Yes or no? Why yes? Why no? Why yes? VGS of which transistor is changing? If VGS of input transistor changes, so let me focus on this a bit. It's a very important concept. If you are saying if I increase VB2, why do you say VGS is changing? I can say that VG is changing. That I can say. Why do you say VGS is changing? You cannot conclude whether VGS is changing, right? So when you say VGS is changing, which means that current is changing. But who is setting the current in this stack? No, VD1 is not setting current, right? So M1 VGS is setting the current, right? The current is constant current bias using I0, right? So essentially the current is constant, which means if I put number of transistors in this stack, all of them in saturation, all of them VGS have to be constant. They cannot change. If I keep moving gate, the source also has to follow. Okay, fine. So that much is clear. So we got a minimum of VB2. Now coming to the maximum of VB2, right? If I keep on increasing VB2, it is expected that the source voltage of M2 is going to increase, right? That's fine. But what's going to break if I keep on increasing VB2? Saturation of M2, right? Because ultimately the current is constant, is expected to be constant. So this voltage is expected to be VDD minus I0 RL, which is also expected to be constant, right? If VD2 is expected to be constant, which means VD2 you cannot increase more than whatever the drain voltage plus one threshold voltage, right? So which means that your VB2 should be less than VDD minus I0 RL minus threshold voltage of the second transistor. Okay. Or the top transistor. Sorry, classification. Yes, thank you. Okay, fine. So now let me probe you a bit further. What happens if I keep, forget about the increasing VBD. So what happens if I keep reducing VBD? Beyond the minimum that we wrote, what's going to happen? Yeah, M1 will go out of saturation, right? So if I reduce VB2, VD1 will come down. But there is only so much it can come down before M1 goes out of saturation, right? So if I keep on reducing VB2, the transistor that I should be checking for is M1. Okay, make sense? Okay. Yes. Question? Okay. Okay, fine. So, so now the question becomes, how do I generate VB2? One way to generate VB2 is obviously through another set of resistances, right? We have voltage divider, and that can be done. But before we stop and I leave you with we meet after mid-sem break, I would like to leave you with a thought that in some cases, so this RDS parameter that we have been dealing with, right? So what was the genesis of that? The genesis of that was this lambda term was a genesis of that output resistance, right? If lambda were 0, then your transistor is the ideal current source. Again, because the transistor current does not depend upon the VDS. The VDS dependence comes because of lambda. Now, depending upon what type of technology, what type of process you are using, the value of lambda times VDS can be quite large with respect to one, right? So, for example, if lambda is let's say 0.2, which is not unheard of, and VDS can swing by 1 volt, which is also common depending upon what type of circuit you are making, then you can see that your IDS can vary by almost 20%. Right? So in some cases that might be acceptable, in some cases that might not. Right? So in cases where it's not acceptable, then you'll have to figure out a way of ensuring that even under the condition that lambda is 0.2 or lambda VDS gives you a 20% variation, how do I keep the condition? right? So that is something that we'll explore when we come back after the technical phase. Okay.
We can ignore channel and modulation.
Yes, so we can, so we do it in two stages. We ignore channel modulation in the first case, right? And then we see that, again, it's basically play on output resistance, right? So, so if you have, this is the childhood for finger transit. So naturally, you know, RDS is not high, right? Lambda VDS becoming dominant in terms means that RDS is low. So the game will be to ensure that the output resistance is. We already saw one topology, how to increase output resistance. So we use that and see what are the effects of this. Okay, thank you.